Hello. In today's video, let's look at an amazing problem. It is a wonderful blend of mechanics, algebra, and geometry. I made a video about 2 months ago about the secrets behind the best free throws in basketball games, in which I discussed the main intuition as well as the main finding. So today, we're going to look at the actual mathematical solutions. Here's our problem. Given the horizontal and vertical separation between the launch point and the target, find the arc such that the impact speed is minimized. Only uniform gravity is considered. So here we have an illustration. The horizontal separation is x, and the vertical separation is y. Both have units of length. And since only uniform gravity is considered, the trajectory of the projectile is a parabola, a fact which I derived in detail in one of my previous videos. Link in the video description. I'll first present the solution and then its justification. First, let's look at a purely geometric solution. We're given the launch point O as well as the target T. The horizontal direction is given by the line OP, and the vertical direction is given by the line TP. And of course, we have PT perpendicular to OP. So the right triangle OTP is given by the geometry of the problem. And here's our solution. We're going to extend the line PT to the point A, such that TA is equal to OT, which is the hypotenuse of the right triangle OTP. Then we connect OA. After that, we draw a line that is perpendicular to OA through the point T. That line will intersect OA at B. So therefore, TB is perpendicular to OA. After this construction is completed, we then claim that OA is the launch direction of the optimal arc. That is the arc with minimum impact speed when the projectile reaches the target T. This launch direction is referred to as the line of launch. The direction of the impact velocity is called the line of fall. In the diagram, it is given by the line TB. And last but not least, we also have the initial launch speed, which is denoted as V naught equals to the square root of g times the length of PA. And here, g denotes the acceleration due to gravity, which is around 9.81 meters per second squared. An equivalent solution given by formulas as follows. In the same setup, let's denote the length of OP to be x and the length of TP to be y. We then calculate the length of the hypotenuse OT, denoted as r, which by the Pythagorean theorem is of course equals to the square root of x squared plus y squared. Then we calculate the size of the angle TOP, denoted by alpha, which is equal to the inverse tangent of y over x. So alpha specifies the direction of the line OT, which is what we call the line of sight. And then the initial speed V naught is given by the square root of g times r plus y. The impact speed V1 is given by the square root of r minus y. So here I combine V naught and V1 into a single formula, where 0 corresponds to the plus sign and 1 corresponds to the minus sign. And on top of that, we have the launch angle as well as the impact angle. The launch angle, denoted as theta naught, is the angle between the line of launch and the horizontal direction. This is given by pi over 4 plus half alpha, measured in radians. The impact angle is the angle made by the line of fall and the horizontal line, denoted as theta 1. Theta 1 is given by pi over 4 minus half alpha. This completes our solution. Let's take a look at an example which applies our solution in the setting of free throw. Example, in our NBA free throw problem, we treat x equals to 15 feet. This is the horizontal distance between the free throw line and the basket. We treat y as the difference between the height of the basket and the player's height. The height of the basket is 10 feet, and the average NBA player height is around 6 feet 6. So y equals to 10 feet minus 6 feet 6 equals to 3.5 feet. With these two pieces of data, r equals to the square root of x squared plus y squared as described, is 15.5 feet, which is equivalent to 4.69 meters. And alpha, which is the line of sight angle, equals to the inverse tangent of y over x, and that simplifies to around 13.1 degrees. Our solution says V naught equals to the square root of g times r plus y. That simplifies to 7.51 meters per second squared. The associated launch angle theta naught is 45 degree plus half alpha, and that simplifies to 51.6 degrees. So now we know how the solution works. We shall then justify it. Here's our plan. We're going to justify our solution in a few steps. First, we will prove an identity that expresses energy conservation. We will then discuss its consequences. After that, we will solve a shooting problem for fixed V naught. The solution to the shooting problem naturally gives rise to an object called safety parabola. And with the help of safety parabolas, we can finally justify the solution to the optimal arc problem. So here we go. First things first, energy conservation. We claim that for a given trajectory RT, which is a vector-valued function, that E, the energy, defined by 1/2 times r dot length squared minus g dot r is constant. So the first term is the kinetic energy, and the second term minus g dot r is the potential energy, where the vector g denotes the acceleration vector due to gravity. And here's our proof. The idea is, if we wish to show E is a constant, we can simply differentiate it with respect to t and show the derivative equals 0. For that, let's recall the equation of motion of projectile motion, which just says the acceleration r double dot equals to g. And here the vector g should have a vector on top. This is a typo. So now let's start differentiating. We write dE over dt, and the first line is just a definition of E. We then distribute the time derivative over the kinetic energy and the potential energy term. Here we also use the trick, which is writing r dot length squared as the dot product of r dot with itself. The derivative of the dot product is given by the product rule, and the derivative of g dot r is simply g dot r dot, because g is a constant vector. And because dot products are commutative, the first term simplifies to the dot product between r double dot and r dot. At this point, we can apply the distributive law, and the whole expression simplifies to r double dot minus g, and then dot with r dot. And because of the equation of motion, r double dot minus g equals 0. So we have the 0 vector taking dot product with r dot, which is of course 0. So therefore, we conclude dE over dt equals 0, and as a result, E does not change over time for any given trajectory. And this finishes our proof for the energy conservation identity. One of the consequences of energy conservation is that it gives a relationship between the initial speed and the impact speed. Because of energy conservation, the total energy at the launch point equals to that at the end point. We adopt the coordinate system as shown, where O is at the origin, at which the total energy is just the kinetic energy, that is half V naught squared. At the impact point T, the position vector r is x and y, and the constant vector g has components 0 and minus g. And the second g here is a scalar, the magnitude of the vector g. If we simplify this dot product, we get the total energy at the target location, which is half v squared plus gy. And this is exactly the relationship between v naught and v1 we promised. Notice that in this relation, g times y is a constant. Therefore, in order to minimize v1, which is our goal, it is equivalent to minimize v naught. So now our goal is to minimize v naught. To do so, let's consider the following problem. Suppose that the launch speed v naught is given, and we also have the target coordinate x and y. What is the correct launch angle so we can hit the target? And also we may ask the question, does the launch angle even exist? And when it does, how many possible solutions are there? So here is our solution. we're going to recall the trajectory formula, which is derived in the projectile motion video. The trajectory is described by a quadratic function. Y equals to the tangent of theta naught times x minus 1/2 of the secant squared of theta naught times x squared. Here I use dimensionless variables, which are variables without unit, meaning that they're just pure numbers. Capital X is defined as the little x divided by L. Capital Y is the little y divided by L. And L is defined as V naught squared over G, taken as the characteristic length of the problem. In the projectile motion video, we've shown that L is in fact the maximum range. So if the projectile hits the target location must be a point on the trajectory. That means the trajectory equation is satisfied when x and y are the target coordinates. So in the equation, x and y are given, and we're left with just one unknown, theta naught. Now we're going to solve for theta naught. To solve for theta naught, let's recall a trig identity, which says 1 plus tangent square of theta naught equals to the secant square of theta naught. This is just a variation of the Pythagorean theorem. And rearrange, which gives something like this. That is the tangent square of theta naught times x squared minus 2x times tangent theta naught plus x squared plus 2y equals 0. The result is a quadratic equation for tangent of theta naught. We can then apply the quadratic formula. The discriminant delta for the equation is 4x squared minus 4x squared times x squared plus 2y, which can then be factored into 4x squared times 1 minus x squared minus 2y. So we then have three cases based on the sign of the discriminant. And because 4x squared is always positive, the sign of delta is the same as the sign of 1 minus x squared minus 2y. I said 4x squared is positive because we treat x as non-zero in our problem. So case number one, if 1 minus x squared minus 2y is less than 0, then the quadratic equation has no solution. Notice the inequality for a condition of this case can be written equivalently as y greater than 1 minus x squared over 2. Moving on to the next case. If 1 minus x squared minus 2y equals 0, then the discriminant vanishes, in which case the quadratic equation only has one solution, or a repeated root, which is tangent of theta naught equals to 2x over 2x squared, which simplifies to 1 over x. We also notice that the condition for the second case can be written as y equals to 1 minus x squared over 2. Moving on to the third case. If 1 minus x squared minus 2y is positive, in other words, y is less than 1 minus x squared over 2, then the tangent of theta naught will have two distinct solutions. The two roots are given by the quadratic formula, which you can see on the screen. At this point, we're ready to introduce the notion of the safety parabola, which we shall see is the key to solve the optimal arc problem. We notice the special role that the curve y equals to 1 minus x squared over 2 plays in our solution above. We denote this quadratic function of x as ys of x, and this is what we call the safety parabola. It is called the safety parabola because, as we shall see, it is a boundary of the region where all possible trajectories can reach. We first notice that the solvability results above can be rephrased as follows. That is, the launch angle has no solution if and only if the target is above the safety parabola, in which case, of course, it means that hitting the target is impossible. The launch angle will have exactly one solution, provided that the target is on the safety parabola. And the launch angle will have two solutions, provided that the target is below the safety parabola. Moreover, we claim that the safety parabola is the envelope of all possible trajectories given a fixed launch speed, meaning that each trajectory is tangent to the safety parabola. And here's our proof. We denote an arbitrary trajectory specified by the launch angle theta naught as y of x theta naught. We then take the difference between ys, which is a safety parabola, and y of x theta naught, that is the trajectory. So after some straightforward simplification, in which we use the Pythagorean identity again, we get that the difference is equal to 1/2 times 1 minus tangent of theta naught times x squared, which of course implies that the difference is non-negative. So here's our conclusion. For all theta naught, ys of x is always greater or equal to y of x theta naught. The equality is attained if and only if 1 equals to the tangent of theta naught times x, which is the condition of the tangent point. And here is a visualization of the relationship between the safety parabola and an arbitrary trajectory. Let's take a look at a more dynamic visualization. So here I am using Desmos, an online graphing calculator. I first plotted the safety parabola, 1 minus x squared over 2. Then on the diagram, I'm going to add an arbitrary trajectory. The trajectory is parameterized by k, that is the tangent of the launch angle. As we can see, the trajectory and the safety parabola is tangent at exactly 1 point. And of course, the two curves will share the same tangent line at that point. I'll then add the line of launch, which is tangent to the trajectory at the launch point. Let's take a moment and appreciate this beautiful animation. This is all well and good, but what does it have to do with the optimal arc problem? And this is where we shall get to next. In our analysis so far, we've been only using dimensionless variables. We can then convert the safety parabola into physical units. Using the definitions, little x equals to big X times L, and little y equals to big Y times L. So therefore, we have big YS times L equals to 1 minus big X squared over 2 times L. And big X is just little x divided by L. This simplifies to 1/2 times L minus x squared over L, which we denote as little y of s. And that is the safety parabola in physical units. So now we have a family of safety parabolas parameterized by L. And here we plotted a few examples of little y of s for L equals to 1, 2, 3, 4, 5 meters. And clearly we can see larger L is equivalent to higher safety parabola. And because L is defined as V naught squared over G, this means the higher the initial launch speed, the higher the safety parabola. And this observation agrees with our physical intuition as well, because a projectile with a bigger launch speed can obviously reach a bigger area. Back to the original problem, now we have enough machinery to formulate a condition for optimality. So in order to hit the target X and Y with minimum impact speed, it is equivalent to minimize the launch speed. This is a consequence of the energy conservation. And to minimize V naught, it is equivalent to minimize L. This follows from the definition of L. And to minimize L, it is equivalent to find the lowest possible safety parabola. That is, the safety parabola that happens to pass through the point xy. Therefore, we plug in xy into the equation of the physical safety parabola. That is y equals to 1/2 times L minus x squared over L. The equation for L turns out once again to be a quadratic equation. That is L squared minus 2y times L minus x squared equals 0, whose only positive root is L equals to y plus the square root of y squared plus x squared. So L is just y plus r. Because L is V naught squared over G, we can quickly solve for V naught as the square root of G times y plus r. And this is exactly the minimum launch speed. We can then use the energy conservation to find the minimum impact speed. Because 1/2 V naught squared equals to 1/2 V1 squared plus 2GY. We substitute the expression for V naught that we just obtained, and we get V1 equals to the square root of G times R minus Y. It still remains to find the angles theta naught and theta 1. This is of course equivalent to finding the slopes of the line of launch and the line of fall. For this, we use the tangent condition. We know that an arbitrary trajectory is always tangent to the safety parabola at exactly 1 point. For the optimal arc, that tangent point is the target location. The tangent condition says the tangent of theta naught times big X equals 1. And therefore, the tangent of theta naught is just 1 over x. which is equivalent to L over little x, equivalent to y plus r over x, equivalent to y plus the square root of x squared plus y squared over x. And this is the slope of the line of launch. To find the slope of the line of fall, let's take a look at our visualization once again. We see at the target position, the safety parabola and the trajectory shares the same tangent line. So to find the slope of the line of fall, we can just take the derivative of the safety parabola and then evaluate it at the target position. So we have the slope of the line of fall equals to minus tangent of theta 1. We use the minus sign because the slope of the line of fall is always negative and theta 1 is taken as positive. This, as discussed, is the derivative of the safety parabola, evaluated at x, the target position. This simplifies to just minus x over L. But we can see immediately this is exactly the negative reciprocal of the slope of the line of launch. This is a highly interesting result because this means that the line of fall is always perpendicular to the line of launch. At this point, the optimal arc problem is pretty much solved, but we can give it a nice geometric interpretation. Let's look at the expression for the tangent of theta naught once again. Tangent of theta naught is y plus r over x. That means in the right triangle OAP, AP is equal to OP times the tangent of theta naught. And because OP in our notation is just x, AP is just y plus r. But also because PT is y, AT is just r. That means AT and OT have the same length. So therefore, the triangle OAT is in fact isosceles. And as a result, the angle A equals to the angle AOT. And the angle AOT is theta naught minus alpha. The exterior angle OTP is therefore the sum of the angle A and the angle AOT. And that is just 2 times theta naught minus alpha. And on the other hand, since the triangle OTP is a right triangle, the angle OTP is 90 degree or half pi minus alpha. This gives an equation for theta naught. That is half pi equals to 2 times the difference between theta naught and alpha plus alpha. Solving it, we get theta naught equals to pi over 4 plus half alpha. And finally, since the line of launch OA is perpendicular to the line of fall TB, we must have theta 1 plus theta naught equals to half pi. So then theta 1 is also solved, equals to pi over 4 minus half alpha. And we're finally done. And just for the sake of completeness, we also give the full equation of the optimal trajectory. Denote x1, y1 as the target coordinates. We can then substitute the expressions for the launch angle and initial speed into the trajectory in physical units. After some straightforward simplification, we get y of x equals to y1 plus r times x over x1 minus r times x over x1 bracketed squared. And this is the full optimal trajectory. And that's the end of today's video. If you like my content, please consider like and subscribe, and I shall see you next time. Bye.